Right, hello. My name is Aiden. I'm going to be presenting my final on the quicksort algorithm. To get started, why use quicksort? So, quicksort is a highly efficient and generally faster than other sorting algorithms like the bubble sort algorithm or the insertion sort algorithm or merge sort, especially if you're going to be using it for larger data sets because it's just quick, it's efficient. It's not the fastest though. Quicksort follows the divide and conquer theory. Divides the array into smaller subarrays based on a pivot element, and then it recursively goes through those subarrays and calls sort again. This approach is great because it handles large data sets by breaking them down into smaller parts, causing it to be more efficient than just trying to brute force the whole thing or creating another array and storing that separately or allocating more memory that way. Quicksort can be implemented in place, meaning it's very memory efficient. So like I was just talking about, it does this by rearranging the elements within the array itself without needing to create extra space for a whole separate array and storing that and then outputting that. This is how it is memory efficient, making it important for applications with like limited memory resources. A couple reasons you don't want to use quicksort. So although we love quicksort because it's a very efficient algorithm, that does not mean that it was without its problems. Quicksort has a worst case time complexity of O of n squared. If the pivot selection consistently results in unbalanced partitions, such as when the array is already sorted or nearly sorted, quicksort can perform significantly slower compared to other sorting algorithms like the merge sort algorithm, which guarantees an O(n) of log n time complexity in all cases, which means that it is also a bit inconsistent. Quicksort is not a stable sorting algorithm. A stable sorting algorithm is important for storing the relative order of equal elements in the sorted output. This means that if you have elements with the same value, their relative order in the input, the original input you put in, may not be the same in the sorted output that it eventually spits out to you. Quicksort performance relies on selecting a good pivot element. If the pivot element selection strategy is poor, such as the first or last element, then quicksort efficiency can degrade. Here's a visualization of quicksort. So it picks a random element, looks like it chooses 5 here, and then it moves that down here, or it moves that, and then it sorts all the things in the subarray before that are smaller, and then all the things after. And then this isn't the best visualization I think of it, but it would create a new subarray with like 4, 3, 1, 2, and then 8, 6, 7, 11, 9, 10, and you would get a new subarray, which then you would get a new pivot element, and you would sort it. So that's the case. It would half again, and then eventually it would get down to the base case, which would be where there's only one element in each of the subarrays, and that's when you have the sorted array. How does it work? This algorithm is a divide and conquer sorting algorithm. It begins by using the partition method, which is going to establish the pivot element, which is used to compare to the other elements in the algorithm. It will loop starting from the pivot element plus 1. So after the pivot element, because I'm starting at 1 in my code, or the first index, and then it ends at the last element, and then it will compare the data to the pivot, and if it is less than the pivot element, it will swap the positions of the pivot and the element at the pivot position and increment the pivot position by 1. Otherwise, it will go to the next index and compare that to the pivot until it has reached the last element in a list, which will exit the loop and swap the pivot element with the current pivot position, and it'll return the pivot position as well, so that we can use that in our next subarray. So then it's going to use recursion to call the partition function on the lower and the upper subarrays, and it's going to partition those as well to get the pivot element, and then that's going to sort until it reaches the base case, which is first is less than last, meaning there's less than 2 elements in the list, which means that the entirety of the list has been sorted at this point. Time complexity. So quicksort has an average case time complexity of O in log n, which is efficient for most practical purposes. Its worst case time complexity is going to be O of n squared, and this is because quicksort typically uses a random pivot element, but in my code we're going to be using the first element in the list. Makes it a bit more consistent, but could make it a bit slower actually, so it's not the most efficient it could be. So I'll open that up And here we are. So we've got a few functions. We've got the swap function. It takes data first and last, and swaps the data at first index and the data at the last index with each other. So here's the initial sort call. Sort just takes the data, and then it calls this function, this sort function. It's a helper function. Starting with this is the range. So first is going to be 0, and last is going to be the count minus 1, so the last index. And then it takes the data. And then if there are more than, or there are at least 2 elements in the array and list, then it's going to call sort recursively until we have a sorted list, which will be the base case. So if this checks out, then we go in here and pivot index is equal to whatever you get from partitioning the data first and last. So we'll go up here. So we got partition. So we got some variables for the pivot index position and the pivot starting value. Int index is equal to the first, whatever this is going to be, and then it's going to be pivot's going to be equal to the data at the first index, whatever that is. So that's going to be our pivot, and then we create a for loop to go through the list all the way to the last index, and then check if the data index I is less than the pivot value. If it is, we're going to increment the index by 1 on the pivot, and then swap the element at the pivot position with the current element at index. Then we're going to continue doing this until we reach the last index, and then we exit this loop, and then we swap the pivot element with the element at the current pivot position, so index and first. Then we return the pivot position, so this can be used recursively. So that's how we start, and now we have it sorted, and we have a pivot element, and we're going to go back down to where we're going to call this again. This is our recursion. It's going to call sort with data. It's going to go first to the pivot index minus 1, and it's going to call sort on the data pivot index plus 1 to the end. And it's going to do that over and over and over until first is not equal to last. Then we know we have the full sorted algorithm that's going to end, and then we're gonna have our sorted array. So we're gonna test that right here. Oh, right there. So here's our test. So we got test 1. We got this sorted array 1, 2, 3, 4, 5, 6, and then we have this unsorted array 3, 5, 2, 6, 1, 4. We'll test that one real quick. Test 1 right here, success, means our algorithm did work, our sort algorithm did work, so it is equal to the sorted array. Test 2, we've got a sorted array which is 1, 2, 3, 4, 5, 6, and this is what we're looking for here. And then we've got a new list of the sorted array, and we quick sort the data, and it should come back with that exact same list. Shouldn't change anything there, because it is already sorted. There you go, and we succeed there. Okay, we're going to test our algorithm one more time on test 3. So test 3 is going to have a sorted array that is empty. Then we're going to try to sort that empty array, and if it comes back empty, then it's a success. So it's a good test. And there you go, that one passes as well. So that is quicksort. Very good algorithm for its efficiency and its simplicity. Yeah, that is my final exam. Thank you, everybody. Goodbye.